Hey everybody, this is Trigonometry. We're going to start looking at radians. This is Math 154 at College of the Sequoias. It might be a different class for you. For us, it's Chapter 6 because we're using a merged book. You might be using something different depending on your school, but this is covering radians, assuming you've already learned how to work with degrees. So for us, it's 6.1, and it's called radian measure. 6.1 and 6.2 really go together really well. I'm going to make them two separate videos, but I recommend watching them both and then doing both assignments at once because they go hand in hand. So what is a radian? So good question. A radian is the measure of the angle when the arc length of a circle, or when the arc length equals the radius. And when I say a radian, I mean 1 radian. A single radian. So let's just take a look at a circle and discuss what this is. I'm going to center the circle at the origin. See how well I can make it. And I'll leave part of it empty because I'm going to do it in red. And so we've got an angle theta here. This is the radius. This is arc length. S is arc length. And it's a portion of the way around the circle. Portion of the circumference. The length of an arc. And for this, for a radian exists when S equals R. So I guess I probably didn't do it very well. I should have made it a little bit bigger. The length here is equal to the length going around. And the way we show it is the general measure for it. We say theta is the proportion of the arc length over the radius. This is for any angle theta. In radians. Okay. If we multiply by R, you'll see the equation S equals R theta. This is the equation for arc length. And in a particular case where we use the unit circle, on the unit circle, R equals 1. And so the arc length equals the length of the measure of the angle. That's pretty deep. So S equals theta. And that's the equation. And where the 1 radian stems from is this. If we go back in to theta equals S over R, and we substitute in S for R, When r equals s, we have theta equals s over s. They cancel out and you have 1. So when r equals s, theta equals 1, it doesn't have a unit. It's 1 radian. And when you have more than 1, it's radians. Sometimes you see the word rads. But that isn't necessary. I'm going to pause it, let you. Well, I'm not going to pause. You're going to pause if you'd like to write this down some more. All right. One second. All right. So where'd my picture go? There it is. So more about that. If an angle doesn't say degrees, or no degree symbol, it is assumed to be in radians. And notice I said theta equaled s over s equaled 1 radian, or theta equaled s over r. S and r have the same units, which cancel when we divide like this. What this tells us is that radians are unitless. So we don't even say them. The only time I specify radians is either when I'm first teaching a subject or when I'm dealing with someone that is so used to working with degrees, I really need to make sure they know I'm not talking about degrees. Okay. So take this a little bit further. Recall a full circle. If we go all the way around the circle, we're talking about the circumference, right? And recall that's 2 pi times the radius. But if we do the full circle, that's also equal to the arc length. The arc length is the distance around the circle, or distance around an arc. This just so happens that we go the full way. So for a full circle, theta equals s over r, which is 2 pi r over r. R's cancel out. Theta is 2 pi. There are 2 pi radians in one complete revolution. Or rotation. People use words for both of them. And what does that tell us? How does that relate to degrees? A full circle in terms of degrees was 360 degrees. So 360 degrees equals 2 pi. We can make 2 unit rates. Make unit rates by making one side equal 1. Or conversion rates. Conversion rates is another way we call it. Makes one side equal 1. So option A, if I divide by 360 degrees, I get 1 equals 2 pi, 1 degree equals 2 pi over 360, or 1 degree equals pi over 180 radians. I'm writing the radians so you know what I'm talking about. In the future, I won't. Option B, we go the other way. We divide by 2 pi. And you'll see that 1 radian is 180 degrees divided by pi. The 360 and the 2 simplify to 180. So 1 pi is 180 degrees. So let's do some practice converting from degrees to radians and radians to degrees. I want to make sure you have that, but it's important you're able to do this. Because sometimes you get stuff in degrees, but there's a reason why we work with radians. And it has a lot to do with the calculus of it. When you start taking calculus, there's a lot of equations that are really, really simple to use in radians. When you use them with degrees, it becomes a terror to memorize. I might actually have this in my lecture notes later. If not, I'll slap a short video together later on to show it out. Let's do some examples. So we're going to convert. Let's start off converting degrees to radians. You're used to working with degrees. Let's start shifting them over. In fact, I think we should do all of our basic ones that we talked about, the 30, 45, 60, and 90. And 0. Why not? 30, 45, 60, and 90. Okay. When we're converting from degrees to radians, we want to get rid of degrees, so it's going to be on bottom. Of the 2 unit rates we want to use the one where degrees are on bottom. If I move the degree down here, it's pi radians over 180 degrees. Multiply this by pi radians over 180 degrees. The degrees cancel. And of course we get 0. 0 times anything is 0. The way I learned how to do these, I actually put vertical lines up. I was taught this is a conversion bridge. As you're going over the bridge, you dump the stuff you don't want over the side because we're polluters. I don't want degrees. I want the degrees on the bottom. And I need the conversion rate where there's degrees on the bottom. There's 180 degrees in 1 pi radians. And I'm writing radians now just to remind you, but I will not in the future. The radians cancel, or the degrees cancel. We have 30 over 180 radians. We can divide both sides, or top and bottom by 10. We get 3 over 18, which simplifies to what? What am I doing here? Yeah. We get 1/6 of a radian. Nope, pi over 6 radians. There we go. That's what's missing. I'm like, this is wrong. Pi over 6 radians. There we go. I'm like, I know it's not 1/6. That doesn't make any sense. All right. So we'll multiply each of these by pi over 180. 45 pi over 180 degrees. This actually turns into pi over 4. The radians cancel again. We have 60 pi over 180. The zeros cancel. 6 over 18 is 1/3. We've got pi over 3 radians. ends up giving us 90 pi over 180, which is pi over 2. They're all nice and simple, easy numbers to remember. There's a pi and one of the first few whole numbers. And I'll actually give you a link later on that you're going to, I really like this video. In class, when we do it in class, I'll do it in person. We've watched the video together because the lady fascinates me. She teaches it really well. But I'll put a link in when we start doing 6.2. So let me give you a couple others. You guys can try them. I'll pause it right there. We're going to use this and make a chart later on. Okay, so why don't you guys try? There we go. Trying to get my camera and my paper the way I want it. You try. So A, we're going to do, let's get rid of the basic ones, switch to something more challenging. Pause it and go ahead and work through these. I'll assume that you did. In each case, we're multiplying by pi radians over 180 degrees. This gets us 249.8 over 180 pi, which does not make a nice, pretty number. So if you throw this in a calculator, I got approximately 4.360. And remember, that is in radians. This symbol right here, a wavy equal sign, this means approximately. Effectively, it means I rounded. That's what approximately means. I rounded to that. What was it exactly? 249.8 times pi divided by 180. 4.359832471. It keeps going. Pi is an unending number. Does not repeat. Great number. And we check the other one. Pi over 180 degrees. The negative doesn't go away. We got negative 270 pi over 180. These are actually both multiples of 90. This is negative 3 pi over 2. And when you pi can stay in there, leave pi in there. Don't convert to a decimal, okay? Because converting to a decimal, you have to round. If you leave pi in, it's exact. And remember, we like exact. Let's practice going the other way. Let's convert radians to degrees. Let's try 9 pi over 4. We'll do negative 5 pi over 6. Okay. So now we're going to multiply. We want to get rid of radians. So there's pi radians in 180 degrees. Radians cancel. 180 divided by 45. And the pi's cancel. This ends up being 9 times 180 divided by 44, or divided by 4, which ends up being 9 times 45, which is that right? Yeah, 9 times 45 is 405, and this is degrees. So more than a circle. Do that here. Pi cancels. 180 divided by 6 is 30. So this is negative 150 degrees. And just a quick recap. What are their reference angles? Their reference angles. We can do them in degrees. Remember, we want to get it where it's the least positive one. So we've got 405 minus 360, 45 degrees. So that's our reference angle. And the other one, we've got negative 150 degrees. We'll add 360 to it. Gives us 210. Where are we at on the circle with 210? We go, that's 180, so 210's in quadrant 3. Theta hat is right there. And for that one, we have to do theta hat is our angle minus 180. 210 minus 180 is 30 degrees. So our reference angle for that one is 30 degrees. Okay. Let's go on. So that thing I was telling you about the calculus thing, I actually do have it and what I wanted to say. In calculus and onwards, in calculus, you will do an action called taking the derivative. The derivative of sine theta in radians is cosine theta. In degrees, it's pi over 180 degrees, or pi over 180 cosine theta. This starts introducing ugly numbers into your problems. If you're working in radians from the get-go, good stuff. So let's look at some more stuff. We have a circle with a radius of 18.20 centimeters. Find the arc length. When A, theta equals 3 pi over 8, and B, theta equals 144 degrees. Okay, that's what we're going to do. Recall I told you what arc length was. Arc length was S equals R theta. And it stemmed from theta being S over R. Theta must be in radians for that formula. It just so happens to already be in radians for part A, so we're good to go. S equals R, which is 18.20 centimeters. We multiply it by the unitless radians of 3 pi over 8. (18.2) times 3 times pi divided by 8. We have 4 significant digits. On my calculator, that will give me 21.44, and the units are centimeters. All right, we'll do the other one. First, we need to convert to radians. We get 144 pi over 180 equals theta. I'm going to leave it as that. So S equals 18.20 centimeters times 144 pi over 180. Throw that into a calculator. 18.2 times 144 times pi divided by 180. 45.74. Did I round that correctly? Yeah, 45.74 centimeters. So that's doing some stuff with an example of it. Let's do one that relates to us on planet Earth. So pause it if you need to write this stuff down. So our next example, we like to think of Earth as a sphere, but Earth is not a perfect sphere. The term for it is oblate. It doesn't have the same radius every direction you go. From the equator it does, but from the equator to the poles, North and South Pole, I think it's a little bit longer or shorter. I forget which one. It's not quite as far. The distance is different. But treating it as a sphere is a pretty good tool. It's pretty close. So we'll treat it as a sphere. For these basic calculations, for classwork. So here's our example. If you look at a map, Reno, Nevada is about due north, straight north of Los Angeles. Reno is at 40 degrees north latitude. And LA is at 30 degrees north latitude. Latitude is like the degrees away from the equator. Not 30, it's 34, sorry. So we draw our little, I'll make a little planet. And that's like the equator. Going around. There's the center. And like going straight to the side. That's the side going up like 34 degrees. Like LA is right there. And Reno is right there, kind of thing. So there's a distance between us on the planet. And we want to find the distance between find the distance between Reno and LA as the bird flies, they say, in a straight line. As the bird flies, which means direct straight line. Roads don't do that. You cannot drive in a straight line from Reno to LA or vice versa unless you're doing it through the air like a bird. And so to do that, we need one more piece of information. The average radius of the Earth is 6,400 kilometers. Okay. That's a nice simple number to use. We do not want to do it in miles. It's a different number. It's crappy. Okay. But doing it in the metric system allows us to shift everything where it's a smaller number. And that's a good, nice, easy number to work with. So to solve this, first question, what is the theta right there? What is the degree, or what is the degree separation between them? Well, 40 minus 34, 6 degrees. So we're going to use, we're looking for this distance right here, and that's portioned the way around a circle. Since it's in a straight line, it's like going around a circle. S equals r theta, which is 6,400 kilometers. We have 6 degrees, but we don't want to leave it as degrees, so we're going to multiply it by pi over 180 degrees. That gets us into radians. 6,400 times 6 divided by 180. Oh, that doesn't simplify well. Let's see, this is, let's do it by hand. Let's get it exact. So 6 times 6,400. No, I'm going to leave it separated. This is like, and there's a pi in there. This, you might find this helpful. I see they both have a 0, so I'm going to treat this as 640 times 10. And this is 18 times 10 on the bottom. And I have a 6 and a pi. And I know I'm going to treat this as times 10. I got an 18, but 6 is a factor of 18. So I'm going to write 18 as 3 times 6. My 10s cancel. My 6s cancel. And I get 640 pi over 3 kilometers, which isn't useful at all. So 6,400 times 6 times pi divided by 180 is approximately 607. We got, this is 2 significant digits. We're going to just round to the nearest kilometer, 670 kilometers. This is approximately 670 kilometers. Okay. That's another example of using something real world-ish to determine the distance between them. Do another example. I'll pause it, let you finish writing this down. So next example, pulley system, engineering and physics. A rope / pulley system is being used to hoist a beam. Hoist or lift a beam. The pulley's radius is a half a foot. And so let me illustrate how that works. We've got a pulley right here. The rope goes over it. And you're down here and you're holding on to it and you're hoisting it. And as you pull on the rope, the beam goes up. Beam. So as the rope moves, the pulley turns. So our first question, how far does the beam move when the pulley rotates 690 degrees? So this pulley is rotating as it's moving. That much of the rope is moving also, but it's on the outside. Excuse me. It's on the outside, so the rope is on the arc length. So we're going to look at S equals R theta again. R is 1/2 of a foot. Theta, it goes through 690 degrees. And we don't want degrees, we want radians. So we're going to do the conversion rate, pi over 180 degrees. And this ends up simplifying down to, if you actually write it out, it simplifies to 23 pi over 12. And if you throw that in a calculator, let's see what that is. I'll do the whole thing. 690 times pi divided by 180 divided by 2, which is the same thing as multiplying by 1/2. It's about 6 feet. S is approximately 6.0 feet. Next question. How many rotations are necessary to lift the beam 50 feet? Okay. Well, here, the 50 feet, I'll pause it and try to figure that out. What is that in the S equals R theta problem? It turns out the 50 feet, if it's on the edge of the pulley, if the rope is moving that pulley, it's moving the arc length that. So S equals 50 feet. But we know 50 feet equals, and S equals R theta. So 50 feet equals 1/2 a foot times theta. I can, we multiply both sides by 2 and divide and cancel out the feet. We get 100 equals theta. But that's in radians. That's not how many rotations it is. To go from that to rotations, theta equals 100 radians. We know for a normal circle, 100 radians, there are 2 pi radians in one rotation. So theta leads to 100 over 2 pi rotations, which is 50 over pi rotations. And we throw that in a calculator. About 15.9. You could argue 16 pretty easy. One more type of problem in this section. This video will be done and I'll do 6.2. And this one is applicable. Area of a sector. So a sector is the region where the region captured by sweeping a line theta degrees, or theta degrees radians. It's an area. We start there, we sweep out an angle theta, and this is the area of that sector. That's called the sector. And how do we come up with the formula? Let's compare area for the sector. So what do we know about a full circle? What is the area of a full circle? You guys remember? It's pi r squared. So let's make a proportion comparing arc length with area. We can put area on top, arc length on bottom. And so we'll do the full circle on like the left side and the sector on the right. We've got pi r squared is the area. The arc length we know is the full circumference is 2 pi r. So area and S. We don't know the area over here, so smiley face. We know the arc length though, it's r theta, right? So we solve for theta, or solve for smiley face. What do we get? multiply that over, what do we got? We've got smiley face equals pi. We've got an extra r on top, pi r cubed. We have a theta over 2 pi r. And we can start canceling stuff out. A pi cancels out, an r cancels out. So smiley face, which is the area of a sector, the pi is gone, one of the r is gone. We've got r squared theta over 2. So the other way of saying it, they often write SA, sector area, is 1/2 r squared theta. Again, S was in radians, so SA is in radians. Well, it has the theta radians for theta. Okay? I'll do one problem with it, and then I'll give an example of where you can think about how you can apply this to real life. Let's see, we've got a sprinkler in the corner of a rectangular yard. Sprays water over the yard in a 30-foot radius. And it doesn't spray anywhere else. Cause like, say it's concrete in the driveway, and it's aimed to not get it on the concrete or the driveway. How much ground is watered? Okay. Oh. There we go. I'm going to shift that even more so I can get to the way over there. That's how I like it, right there. All right, so let's draw a picture. We've got a rectangle yard. Let's say that's the driveway. And your house is right here. And the grass is right here. And our sprinkler's right here. And it sprays out in a 30-foot radius. And so it's hitting everywhere in here because it rotates. Water sprays out in that. Some of them rotate, some of them just spray in general. So it looks like we're looking for the area of a sector. So the area of a sector is 1/2 r squared theta. What is theta here? We have r, right? R is given to us at 30 feet. What's theta? Theta is, it looks like a quarter of a circle, which is 90 degrees. But we don't want 90 degrees. Theta is pi over 2. And we did that earlier. So we have 1/2 times 30 feet squared times pi over 2. 30 squared is 900. Then we got a pi. Feet, we square feet, we get square feet, which is an area unit. And on the bottom, we got 2 times 2 is 4. This is 225 pi square feet, which is not all that helpful. Oops. Times shift pi. 706.858. $8583471. The starting stuff was in terms of feet. Let's just do it in feet. Rounded to the nearest foot is 707 square feet. Or square feet is listed like that as well. Okay, where does this apply to you? This may not apply to you. I've brought this up in class, and every once in a while I get a student that for some reason or another doesn't like pizza. Okay, so you could actually go through it if you know the size of the pizzas. Is 3 slices of a medium pizza more or less than 2 slices of a large? Now, to do that, you have to know some certain things. Yeah, you'll need to know, must know the radius of the pizza. And when they tell you like a 14-inch pizza, that's usually the diameter. Okay? Because otherwise, a 14-inch, like a large is a 14-inch pizza, that's 12 inches, which is, if I put it up against my head, I've never had a piece of pizza that is longer than my head and a little bit longer. So when they tell you pizza, or they give you the sizes in pizza, pizza sizes are in diameter. Good to know. And you also have to know how many slices there are in each pizza, number of slices, and assume equal size. And how often do the pizza places cut a pizza with equal size slices? They don't. They're going through it quickly, so some slices are a little bit narrower, some slices are a little bit wider. Now I want to have pizza for dinner. Damn it, I wish I hadn't talked about this. All right, that is 6.1. I'm going to lead you into 6.2 in the next video, but I want to put up something. You might want to write this down. I will actually have this in Canvas as a clickable link, but I'll have it in the notes as well. This will be the start of our next page. This is what I'm going to start 6.2 video with. If you go to calcworkshop.com, let me see if I can put this up on the screen, show you where to look. Calc Workshop Unit Circle. There we go. I'm going to change what I'm sharing with you. So let's share the internet. So I am at that page. This is Calc Workshop. You scroll down to the bottom. This is about unit circle. They've got a lot of worksheets. I'll give you the worksheets as well. I've printed them out. I've edited them a little bit. They actually show you, these are the values with sine and cosine. We're going to talk about this in 6.2, the values of the sine and cosine for each of these. but it shows you all the degree marks on the circles, the major ones that matter. And then on the outside, it shows you the radians. So all these colors are in radians, 2 pi over 3, 3 pi over 4. And if you come down to the bottom, she actually talks about it right here, but if you don't want to read it, come down to here. It actually tells you where to look. It says 23:51 to 46. If you go from like 24 minutes to 46 minutes, like I said in the other thing on the video, just scroll up to start at 24.
Unit, sir. And I don't have anything to keep them straight. Do I have to use color coding? No.
She's going to show you a great way to memorize the unit circle, where the degrees are, the radians are, just using your left hand. It's only using your left hand. It's 20 minutes. This whole video is, let's see, it's an hour and 30 minutes. She actually goes through a lot of examples. It might, if you have the time, watch the whole thing. If you watch the whole thing, you will have this trig thing down. She's really good at explaining it. I really love her left hand thing. Definitely watch this 24 to 46 minute video. And I will put that website up again. We got this. That's it. This is all one thing. I couldn't write it out well. And it's the unit circle video near the bottom, and it tells you where to do the trick. After that 46-minute mark, she literally does like an hour of examples of calculating sine and cosine for different angles, weird angles and stuff like that. You go watch that, you'll get this. You will get this. And she does it so well, I don't want to re-waste your time by doing it again because she does it well. I will have 6.2 ready in a little while. Now I want to go eat pizza. So I'll go figure something out and I'll be back. Peace. Take care, friends. Stop the sharing and